Continuing on with Unit 6, in this video we're going to talk about learning target 7b, which is all about exponential functions. By the end of this lesson, you will be able to identify all transformations of an exponential function, including how to identify where the horizontal asymptote has moved to, and describe what the graph looks like using domain, range, as well as the horizontal asymptote. So let's review our transformations. So in this section, our parent function is going to be y equals b to the x, where b is the base of our exponential. And as we learned in our last learning target, the value of b depends on if we start with an exponential growth or an exponential decay graph. So here we don't just have really one parent function, we actually have an infinite amount of parent functions depending on what the base is. But we have two types, this exponential growth base, if we have that parent function, versus the exponential decay. So our four transformations are the same transformations we learned about during first semester. Our first transformation is the horizontal shifts, and that happens when I shift the graph to the right or to the left. Remember, that transformation is what happens inside the function. Since our variable now is in the exponent in our parent function, then inside the function means that I'm going to be changing what the exponent is equal to. So if I want to horizontally shift to the right h units, that would mean that my equation would be b to the x minus h. If I want to horizontally shift to the left h units, that would be b to the x plus h. And remember, this is technically x minus the negative h there, and that's why it's going to the left, because h itself is a negative number. Our second transformation that we would apply in order is the vertical stretch or compress. So that's what's our slinky from last semester, stretching the graph vertically or shrinking the graph down. That happens when we have this scalar that's multiplied out in front. And we've seen this equation before with y equals a times b to the x. That's actually the more generalized form we talked about in the last learning target. Now this will be a vertical stretch if the absolute value of a is greater than 1. And it will be a vertical compress if the absolute value of a is less than 1, but then still bigger than 0 because of the absolute values. Now, if we had a being negative, that's what takes us to our third type of transformations, which are our reflections. We have two types of reflections: reflections over the x-axis and reflections over the y-axis. If we have a being a negative number, meaning we would multiply by a negative 1 in front of our b to the x, that's a reflection over the x-axis because we're multiplying all the y values by a negative 1, which is flipping them down. Versus if we have a negative sign inside the function, so inside the exponent, and have b to the negative x, then that's a reflection over the y-axis because it's changing all of the x values and making them negative, so that would be flipping it over the y-axis. Our last type of transformation is vertical shifts, and this is what happens if we're going to move the graph up or down so many units. Now this happens outside the function, so this is what happens when we're adding or subtracting a number after the parent function. So if we want to go up k units, it would be y equals b to the x plus k, and if we want to go down k units, it would be y equals b to the x minus k. Now for reference here, I do have the exponential growth graph drawn. So this would just be y equals b to the x, where that b value is bigger than 1, as well as the exponential decay graph drawn, which would be y equals b to the x when b is less than 1, but still bigger than 0. And we want to talk about how these transformations is going to affect the key information on our graph. So we need to know about 3 pieces of information in order to figure out what these graphs are going to end up looking like. We need to know what the domain is, the range, as well as the horizontal asymptote. Well, our domain for any parent function, whether it's an exponential growth or decay, was always all real numbers, because we could plug in all the negative x values, we could plug in 0, and we could plug in all the positive x values. And for the parent function, our range was strictly positive numbers. Since we had this horizontal asymptote on both the growth and decay graphs at y equals 0, then our range was anything above that, since the graph got really, really close to the horizontal asymptote but did not cross or touch it. So for our parent function, this was what our domain and our range was starting with. Now, these are going to get affected depending on what types of transformations we have. Well, our domain, since we're starting off with all real numbers, doesn't matter what type of transformations we do to this, we will still always have a domain of all real numbers. The range, however, is going to get affected. So let's go through each of these. For our range, remember it's affecting our y values. A horizontal shift is moving the graph left or right. That's affecting the x values. So a horizontal shift is never going to change the range. A vertical stretch and compress is stretching the graph vertically, so it is changing the y values, but it's multiplying the y values by that a value. Well, if I multiply 0 times any number a, I'm still always going to get 0. So although the vertical stretch or compress does affect the y coordinates, it's not going to affect the range, since 0 times any number a is always still going to be 0. However, if we have a reflection, specifically a reflection over the x-axis, that's going to change the inequality. So if I take either of these graphs, either the growth or the decay graph, and I flip them over the x-axis, they're going to now be underneath that horizontal asymptote. And in turn, that would change the range and make it y is less than 0, or maybe another number if we have some type of horizontal asymptote change as well. Now the last type of transformations, being the vertical shifts, that's going to change where the horizontal asymptote lies. So if I take a graph and I move it up so many units, it's not only taking the curve, but it's also taking the horizontal asymptote with it, because that horizontal asymptote dictates how this graph curves, and if we move the curve, the horizontal asymptote goes with it. So our range then depends on two things. If we have any vertical shifts, that's going to change the number on the range, because the range was based off of the horizontal asymptote. And if we have a reflection over the x-axis, then that's also going to change the inequality symbol and make it y being less than whatever number we have instead. Now the horizontal asymptotes, we've touched on this already, but for the parent function, they started off at y equals 0. And as we just described, the horizontal asymptotes, I am going to shorthand that with HA for a lot of the writing that I do in this video, just so you guys know, HA is standing for horizontal asymptote. And those horizontal asymptotes do depend on the vertical shifts. So if I take a horizontal line, and if you think about it, you could take your pencil sideways and make it like a horizontal line. If you do a horizontal shift, it just moves the pencil side to side. So that didn't move it up or down, it's still staying in the same horizontal region. Now if I stretch or compress, since I'm starting at y equals 0, although I'm multiplying that a value times 0, 0 times any number is still going to keep it at 0. Now if I do any reflections, if I reflect over the x-axis, well, the horizontal asymptote is on the x-axis to start off with, so if I reflect it over itself, it didn't move, it stayed in the exact same spot. If I reflect it over the y-axis, it still stays in the same spot. Technically the two sides flip-flop, but it's still at y equals 0. However, if I vertically shift it up or down, that is definitely going to move that horizontal asymptote. So our horizontal asymptotes depend on our vertical shifts overall. Let's go through a couple examples. So in each one of these, we're given an exponential function. We want to find quite a few things. We want to find the parent function, determine if the parent function is an exponential growth or decay, because that will help us graph it. We want to state the transformations, the horizontal asymptote, the domain, and the range. We will then use this information to sketch a graph of the function, including the horizontal asymptote. So let's start with our first problem here. We have y equals 4 times 5 to the x power. And we want to start by identifying our parent function. Our parent function, remember, is just that b to the x. So why don't you guys pause the video here and identify what the parent function will be. So for this case, our base of our exponent is 5, so our parent function is just y equals 5 to the x then. Now that we have our parent function, we can use what we learned in our last learning target to determine if this is an exponential growth or decay. Why don't you guys pause the video and write down if this is an exponential growth or decay. So in this case, we have an exponential growth, and that's happening because our base, which was equal to 5, is bigger than 1. The next thing we want to list is any transformations that we might have. And transformations here get a little trickier because we have numbers that are going to change in every single equation because the base can change. So what I like to think about is if I highlight exactly what my parent function is, that 5 to the x, the transformations are coming from anything extra in there. So in this case, the 4 is the only thing that's extra. Because that's being multiplied to my parent function, that's going to be a vertical stretch or compress. Now, will multiplying by 4 vertically stretch the graph or vertically compress it? So since 4 is bigger than 1, this will be a vertical stretch. And to be very specific, it's a vertical stretch by 4. Okay, the next things we have to find are the horizontal asymptote, domain, and the range. So let's start with the horizontal asymptote. We know for any parent function, it's starting at y equals 0. And if I vertically stretch it, well, if it's at y equals 0, vertical stretch means I multiply y by 4, but 0 times 4 is still 0, so my horizontal asymptote stays at y equals 0 then. My domain, since we have an exponential function, my domain of any exponential function is all real numbers. So I can write AR in for short, or if you want to do the negative infinity to infinity and use interval notation, that would work as well. Now the range is dictated by two things: if I have any vertical shifts and if I have any reflections over the x-axis. Another way to help me find the range is it's coming from that horizontal asymptote. Those two are very much intertwined. My range definitely deals with y, and whatever number is in my horizontal asymptote is still going to be the same number that's in my range, because that horizontal asymptote is what this graph is getting really, really close to. So if I have a horizontal asymptote at 0, the range is dependent on that. Now for this example, since there were no reflections over the x-axis, my range is still staying as y is greater than 0. Again, there is no equals to sign on this because my graph does not touch that horizontal asymptote. Okay, let's go ahead and graph this now. So this is going to be a rough sketch of the graph. In fact, I'm not going to have any exact points on this graph at all. I just want to have an idea of what the shape of this graph looks like overall. What I do need to include, however, is the horizontal asymptote, and that needs to be labeled on my graph as well. Now, I didn't provide any coordinate planes because a lot of these graphs look very different from one another depending on the transformations. So let's start with the parent function. So our parent function was 5 to the x. We know that that is an exponential growth graph. So I'm going to draw that graph right here. So I've got an x, I've got a y-axis. Since it's growing, it's starting way down here and getting bigger over time. Remember, it had a horizontal asymptote at y equals 0 to start. So this is what the parent function looks like. And you guys will be expected to kind of sketch the parent function and then have our final kind of transformation graph. And I'm going to draw it to the side, but to have more space in your notes, it might be a good idea to kind of draw it below and go down where the horizontal asymptote, domain, and range are. So let's draw another set of axes here. The only transformation was to stretch this graph vertically by 4. So what that's doing is it's stretching all the y components like a slinky, and it's multiplying each one of those y components by 4. So way down here on the left-hand side, it's still getting really, really close to this, but over time, it's just growing faster. So I can notice that I'm crossing the x-axis now at a much higher point. Now we could substitute in points and find exact points on this, but we're more interested in what's the behavior of this graph and what's the overall picture versus exact points on here. The horizontal asymptote was not affected by the stretch, so I can go ahead and draw that dotted line in again. Remember, represents that horizontal asymptote, and I'll go ahead and label it. And we can always check our work with the domain and range. Domain is all real numbers, which is why the graph has arrows on both the left and the right side, because it keeps getting closer and closer to 0 on the left side, and it keeps getting bigger and bigger on the right side. And the range, being y is greater than 0, is why the entire graph is above that horizontal asymptote then. Okay, let's look at another example. So here we have y equals 3 to the x minus 1 minus 4. Why don't you guys pause the video right here and decide on what your parent function is. So our parent function, remember, is that b to the x. So in this case, my base is 3. So I'm going to end up with y equals 3 to the x as my parent function. Now, will that be an exponential growth or decay graph? So in this case, the parent function is still an exponential growth, and that's happening because that base, which is 3, is bigger than 1. Now we need to identify our transformations. So I know for sure I have at least one transformation because my original equation is not just 3 to the x. Why don't you guys pause the video here and determine how many transformations we have. So in this case, we have two transformations. We have that -1 that's happening in the exponent, and we also have this -4 that's happening outside the function. So we're going to need to list both of those. Why don't you guys pause the video and list these two transformations in order in which we would apply them. So remember, our first type of transformations would be any horizontal shifts. In this case, we do have a horizontal shift. That's because of the x minus 1 in the exponent. And it's telling me that we are going to the right one. So that's our first transformation. The next type of transformation would be any vertical stretches or compresses, but we don't have anything multiplied to the 3 to the x, so I don't have any of those. I also don't have any reflections because there's no negative sign out front and there's no negative on the x. The last type of transformations is our vertical shifts, and that -4 is telling us that we are going down 4. From here, that's really changing what this parent function graph looks like. And sometimes maybe it's a good idea to draw a rough sketch of the parent function to start off with and think about how this could change. So let's start by sketching the parent function. Since it's an exponential growth, we know it starts really small and over time it grows and it gets bigger and bigger and bigger. So that's that y equals 0. That is our horizontal asymptote to begin with. And again, this is that parent function. It's a rough sketch of 3 to the x. From here, let's think about how this graph moves. Well, if I go to the right one, well, that didn't change much of anything. The graph did technically move, so let's draw the new one where I go to the right one. The horizontal asymptote, though, in this case, which is the next thing we're trying to find, doesn't move at all. If I just shift to the right, it's still staying at the same point. I've just slightly shifted this graph a little bit more to the right. The next thing I need to do is go down 4, though. Well, if I go down 4, that's definitely going to move some pieces. Because what's happening is that horizontal asymptote that's at y equals 0 has to move down 4 as well, since it's really, although it's not a point on our graph, it is connected to the shape of our graph. So that means that horizontal asymptote needs to end up way down here then, at y equals 4, versus, at y equals 0, where it started with. And not at positive 4, it would be at -4, since we went down. So that's telling me that I have a horizontal asymptote then, at y equals -4. Now the rest of the graph would move down with it. It would still have the same curve where we're growing over time, it's just now shifted down 4 units. Well, looking at this, my domain is still going to be all real numbers, because I still have all the negatives, x's I could sub in, 0, and all the positive x's. The range, however, is going to change. I'm no longer just looking at everything above 0. Now, I have a range of y is greater than -4. Since as the graph shifted down, my range got to include all those values from 0 to -4. Now, just like before, we don't get to include -4 because that's where the horizontal asymptote is at, and the graph does not cross or touch that horizontal asymptote. So in this case, we actually kind of drew the graph first to get a sense of what the horizontal asymptote domain and range are, versus last time we found that information first and then drew a graph. All these concepts are interconnected to one another, and whichever way is more helpful for us to determine, we can do the problem kind of in any way we want. We just have to make sure we're answering the entire question. Let's look at a third example. So here we have y equals -3 times 2/7 to the x plus 9. Well, just like before, I have to start with my parent function, because that's really giving me the starting shape of my graph that I have before I apply any transformations. So why don't you guys pause the video here and decide on what the parent function is going to be. So for this example, our parent function is going to be y equals 2/7 all to that x power. And I am putting parentheses around it just because the whole 2 over 7 is the base. It's not just the 2. So I want to make sure it's clear that that whole 2 over 7 is my base. Now, will this be an exponential growth or an exponential decay? So in this case, we do have an exponential decay for our first example that we're seeing today at least. So our base in this case, which is 2 over 7, our base there, which equals, there we go, 2 over 7 is less than 1, and that's what's making this an exponential decay. So if we were to start off by drawing what this graph would look like, for the parent function at least, not the final graph, this would be starting up way high and losing kind of steam over time and growing down. And we still, though, have that horizontal asymptote at y equals 0. And again, this is that parent function graph. We'll see how it changes once we determine all the transformations. Why don't you guys pause the video here and decide how many transformations we have for example 3. So in this case, we're going to have 3 transformations, and let's go through each type. So the first type we could have is our horizontal shifts. That would happen if I'm adding or subtracting anything to the exponent, which I don't have in this example, so I don't have any horizontal shifts. The next type of transformation would be if I had any stretch or compress, and in this case, that -3 in front is actually giving me 2 separate transformations. The negative sign is going to be a reflection, which we'll come back to. The 3 itself, though, so the absolute value of -3, is giving me that vertical stretch or compress. And in this case, it's a stretch by 3, since the absolute value of -3 is bigger than 1. So we have to remember that that negative sign is not really telling me anything about the stretch or compress. That's giving me the reflection, which leads us to our second transformation, which is a reflection over the x-axis. And our last type of transformation is those vertical shifts, and that's the +9 in this case, which is telling us to go up 9. Well, let's try to find the information before we graph the final one. Looking at our parent function, if I stretch by 3, well, that just stretches the graph taller, but it doesn't move the horizontal asymptote. If I reflect over the x-axis, that's going to flip the graph underneath the horizontal asymptote, but the horizontal asymptote will still stay in place. But lastly, if we go up 9, that's going to shift the horizontal asymptote up to y equals 9. So the horizontal asymptote will move in this case. Our domain, no matter if I do all those things to it, stretch it, flip it upside down, and then move it up, our domain is still going to be all real numbers because I'm not changing, I didn't stop using any of the x values. I still have all the negatives, still have 0 and all the positives. Our range, however, is going to change. Now we know that it's connected to our horizontal asymptote. So if our horizontal asymptote is at y equals 9, our range should be y is something compared to 9. We need to figure out if it stayed as y is greater than 9, or if maybe it became y is less than 9. Well, when we stretch the graph, it just grew the graph taller, but it's still above. But when we reflect over the x-axis and we flip it down below, it's making the entire graph underneath that horizontal asymptote, which is what's making the range y is less than 9 in this case. And we're going to go through and graph each one of those steps. So our first graph from here was really just that stretch. It didn't change too much of the shape. It made it a little bit less curvy. With my not so exact graphing, it's not going to look much different, but there's our stretch. It's still kept it at y equals 0. From here though, I'm going to go diagonal. Now that we're going to reflect, oops, let me have enough room to reflect over the x-axis. Now that we're going to reflect over the x-axis, instead of it being above the x-axis, it's now going to be under, and it's growing closer to it over time. And we have that horizontal asymptote, though still at 0. And this one we have to think about it. On the left side of the graph here, it was really far away from the x-axis, which is why it's still really far away from the x-axis when it gets flipped down below. So it's literally taking that mirror image, like if you were to draw the graph on your piece of paper and then fold your paper right over that x-axis and make a stamp, you would get this mirror image down here that starts really far away and then gets closer to the horizontal asymptote as we move from the left to the right side of this graph. Now from here, our last step is to go up 9. So we're going to take the same curve shape and move the whole thing up 9 instead. And that's what's moving that horizontal asymptote. So we're now up here, dotted line. So we're now up here at y equals 9. But we still have the same shape, starting far away, and it's curving towards that horizontal asymptote. And if we check it, our horizontal asymptote lines up at y equals 9. Our domain is still all real numbers, but our range is now y is less than 9 in this case. And again, these graphs are just sketches. We want to understand the behavior of what's happening. A calculator could graph this for us, but we need to have some type of internal understanding about, well, if I move all these pieces with the transformation, what happens with that graph in the end? In later math classes that we're going to take, it's going to be less about the individual points and more about the behavior of the overall function and looking at what's happening in the graph from a global perspective versus getting too nitpicky about points that are on the graph. And we could always use a calculator to graph these if we wanted to know what the exact points were. Okay, let's look at our last example here. So in problem 4, we have y equals 1/2 times 8 to the negative x. Why don't you guys pause the video here and decide on what our parent function is going to be. So for this example, our parent function is going to be y equals 8 to the positive x. So that negative sign up there, although it's attached to the x, is not part of my parent function. That's actually going to be one of our transformations, so we'll come back to that in a little bit. Knowing our parent function, do we have an exponential growth or an exponential decay? So we're back to having an exponential growth, and that's happening because our base here is bigger than 1. How many transformations does this example have? So in this case, we're going to have 2 transformations. The 1/2, so that 1/2 is a transformation, and so is that negative sign. In order in which we would apply them, our first transformation would be that stretch or compress, which is coming from that 1/2. Will this be a vertical stretch or vertical compress? So this case is going to be a vertical compress by 1/2, and that's happening since 1/2 is less than 1, so that's why we're compressing or shrinking the graph down. Now this negative sign is a reflection. What type of reflection is this? So this is a reflection over the y-axis. And the reason it's a reflection over the y-axis is because the negative sign is being multiplied to the x itself. And because of that, it's changing on the coordinate level all of the x's to become negative, which flips the graph over the y-axis. Let's draw the original kind of parent function here. And again, this is just a rough sketch of it. So we have that horizontal asymptote that every parent function has starting at y equals 0. Since we have a growth, I'm starting from really close to the asymptote and growing away from it over time. Now, our first transformation is going to compress this by 1/2. Well, that's just shrinking the graph down. It's meaning that the steepness of it is going to take more time to grow over time. That doesn't move the horizontal asymptote. Now, if we reflect over the y-axis, it's flipping the graph kind of as we open a door. So I'm flipping this graph over the y-axis here. Well, the horizontal asymptote stays the exact same. It just kind of flips over itself, and the right side goes to the left side, and the left side goes to the right side. But it's still going to stay at y equals 0. Our domain, just like any exponential function, will always stay at all real numbers. Our range, we know, is connected to our horizontal asymptote, so I will be comparing y to 0. Since we're reflecting over the y-axis, it's keeping the entire graph above that horizontal asymptote, so our range stays at y is greater than 0. Let's sketch out what a little bit of the final function would look like. So our first step is going to be to compress it by 1/2. That's really not going to change much of this graph at all. It's just going to keep it closer to the x-axis longer. So we still have that horizontal asymptote, and it's just going to take more time to slowly grow over time. Then from here, when we reflect it over the y-axis, if we draw our axes again, well, that horizontal line just flips over itself, but it still stays at y equals 0. But the rest of the graph, instead of starting close and going away from the x-axis, it's going to now start away and grow closer to the x-axis over time. And so what this is doing is taking a parent function that was an exponential growth and making it look like an exponential decay because I flipped it over the y-axis. Now, one thing I do want to point out is this question about growth or decay, it is only referring to the parent function. Once we start having so many different transformations to a graph, we can't really classify an exponential function as a growth or decay. That just refers back to the parent function itself. So when we learned about growth or decay in our last unit, we'll notice that we were only looking at equations that were y equals a times b to the x, and we also had the restriction that a had to be a positive number. And the reason that is this would only be a vertical stretch or compress. That's the only type of transformation we could have if we're talking about growth or decay for the final function. And so because of that, this growth or decay question is here to help us remember what the original parent function looks like. Using that parent function sketch of a graph, we can then figure out what the final function would look like from there. So in this video, we learned about how we can connect all of our transformations that we've been talking about all year to now exponential functions, and how that changes the domain, range, and horizontal asymptote as we apply these different transformations to each of the parent functions.